Welcome to the content material for Class 24 of Engineering Statics. You should be watching this video before your 24th class. In this lesson, we will learn how to solve dry friction problems that involve wedges. Wedges can be used in two different ways. A wedge with low friction can be used as a simple machine to slide and move an object. A wedge with a high friction can be used to hold things in place, like this doorstop. For example, consider this situation where a block is sitting on top of a wedge. The wedge could be used to raise the block up if we push on the wedge. In this case, we want the friction coefficient to be low. On the other hand, the wedge could be used to prevent the block from going down. In this case, we want the friction coefficient to be high so that the friction can prevent the wedge from sliding out. When setting up wedge problems, it's important to make all normal forces perpendicular to the surface, as shown here. Also, each object needs to have its own free body diagram, such as this wedge and this block, each will have its own free body diagram. And when drawing the corresponding forces, so this friction force and this friction force, for example, it's important to make those forces equal and opposite across the objects. So for the wedge here, this friction force between the wedge and the block points to the left, but the corresponding force, F2, on the block is pointing in the opposite direction to the right. And the last thing to consider is the impending motion. Depending on whether this block is being pushed or it's not being pushed and the weight is pushing down, we have to consider what is the motion that the wedge may be trying to move, and therefore draw our friction forces are going against the impending motion, just like is shown in this diagram. So let's look at an example of that.
Okay, in this example we have a wedge. We actually have two wedges here with a 3 kilonewton weight sitting on top. And so the way to solve wedge problems is that we need to draw a free body diagram for each of the objects. So I'll start with the bottom wedge, and I'll call this diagram B. So we have the pushing force, and we have the normal force pushing up. We also have a normal force pushing from the other wedge. And remember that it needs to be perpendicular to the surface, and this is at a 15-degree angle. On this surface, there is no friction because we're told that there's rollers there that are frictionless, so we don't have to consider friction on this surface. However, on this surface, we do have friction between the two wedges. So let's draw our other wedge, and I'll call that wedge A. So we have the normal force. So it's equal and opposite. These two forces are the same, equal and opposite pushing against each other. In the same way, we will have equal and opposite friction force. We have the weight pushing down, and there's a normal force from the wall, but no friction because of the rollers. I will help myself with a little bit of trigonometry to make sure I know whether to take the sine or the cosine, since we're at a 15-degree angle. Okay, now the issue that we'll have is that there's still more unknowns than the number of equations that we could make. So there's one unknown, two unknowns, 3, 4, and 5. And there's only 4 equations we can make based on x and y equilibrium for the two free body diagrams. However, there is one more equation we have, which is the fact that we know that the highest force will occur at the impending motion. So we know that the friction between the two blocks is going to be equal to the static friction coefficient times that normal force. So we're going to start with this and call that equation 1. And then for each of the free body diagrams, we can create 4 more equations. Starting with x, I'm going to call this equation 2. So looking at this diagram here, in the x direction, we have this force. We have the x component of the friction, and we have the x component of this normal force. We'll get our next equation from the y equilibrium of that diagram. Okay, next I'm going to move on to my next free body diagram. So we're going to be looking at this free body diagram. Again, we'll start with the x components and the y components and put together our different equations. In the y, call this equation 4 and equation 5. Okay, so moving on, we have to now combine some of the equations. So if we look at equation 3 here, I see that we can solve for NAB by combining equations 1 and 3. So we'll bring together equations 1 and 3. So when I put these numbers in, I'm able to solve that normal force between the two wedges would be a little bit more than 3 kilonewtons. I can go back to my first equation and now solve for the friction force between them. And now since we're only wanting to solve for P, we can just skip straight to equation 4. And we see that we can directly solve for P. I see that P is 2.2 kilonewtons. So what we're seeing in this case is that the force P would be enough to overcome the friction force between the two wedges A and B. And that once the force P gets greater than that, it would force that first wedge A to slide underneath of B and lift up the weight.